Hello everyone, I decided to record a separate video for the examples so that the lesson wouldn't be as long. Well, at least you wouldn't have to watch a very long video. This one I'll try to make it shorter. And for the previous example, sorry about that, we had to draw a free body diagram and show the net external force. I omitted this part and just showed you how to draw the free body diagram. Okay, so now how do we show the normal force? Well, we have the book resting on the table. Here's our free body diagram. The next step would be to decide what's positive, what's negative. It is up to you. I just like to, if there's no motion, I like to keep it simple. Up is positive, down is negative. Okay, next I have to ask this question. Is the object accelerating? Is the object, or let's say the system, in this case it's an object, but let's call it system. Is the system accelerating? Well, clearly the answer is no. Okay, so when the answer is no, this follows. Then we know that the net force, which is equal to the sum of the forces, should be 0 because there is no acceleration. Okay? So then what we need to do is we need to show the forces acting on the book. And what we'll do is the summation of the forces of this force vector is going to be the sum of the forces acting along the x. Oh, I forgot the summation symbol. The summation forces acting on the summation of the forces acting on the x plus the summation of forces acting along the y. Okay? So what this means is, let's start with the summation of forces acting along the x direction. That's horizontal forces. Well, there's none. No push, no nothing, right? There's no forces acting horizontally. So that means the summation of the forces along the x is 0. Now let's try the y direction. Well, we can see we have two forces acting along the y direction, the vertical direction, the weight and the normal force. And we said that normal would be positive and the weight would be negative. So then we have normal force, let's try that in again, minus the weight of the book, the force of weight, because negative because it's going down, pointing down, and that's equal to 0. When my net force is equal to 0, both of these have to be equal to 0. Okay? Now, let's try the second one. A student pushes a box across a classroom. Okay? For this one, man, I didn't notice I didn't draw the free body diagram, but we would just have to recreate this, these four forces to the side. Let me do that. Okay? So sorry for those of you who already watched the other one that it didn't draw the correct free body diagram. There you go. Now let me just get rid of all this stuff. There's my free body diagram. Now let's decide what's positive, what's negative. Keep it simple. Up is positive, down is negative. And when there's motion, in this case, this is moving to the right. This is accelerating toward the right. Okay, this is important. I like to keep the direction of motion positive. So if I have an acceleration to the right, I like to keep it positive. You don't have to, but that's my suggestion. Okay? Whatever the direction of motion is, keep it positive. All right? Keep it positive. Okay. So now, let's sum the forces over here. So we'll have Oh, let's ask the question. Is the object accelerating or is the system accelerating? Is the system accelerating? Well, the answer is yes, because we have this acceleration vector shown to the right. So then that means that the net force, which is equal to the sum of the forces acting on the system, is equal to mass times acceleration. Whenever your system is accelerating, the net force, the summation of the force vectors, has to be equal to mass times acceleration. Okay? So then that means that the sum of the forces, meaning the forces acting along the x plus the forces acting along the y, has to be equal to mass times acceleration. Okay? Now, let's start with the forces acting on the y for this one, okay? Because for this example, one of these two, only one for this example, okay? One of these two has to be equal to mass times acceleration, and the other one will be equal to 0. So then, let us start with the y direction. Forces acting along the y, where we have the weight and normal force. The acceleration vector points to the right, not up, not down. So there's no acceleration in the y direction, which is to say, normal force is positive minus the weight negative is equal to 0. Now, let's think about the forces acting along the x direction. Well, we said this one is positive, the applied force by the student, and frictional force is negative. Acceleration is toward the right along the x direction, which means my summation of forces along the x direction will be equal to mass times acceleration. So we said the force applied by the student is positive minus the frictional force negative. Okay? And this is how you show the net force. In this case, the net force is along the x direction, and then we'll have to do some mathematics to find whatever they want us to find. Okay? But this is how you set it up. This is how you set it up. Every time you draw a free body diagram, this should follow. Now I want to move on to this. Oh, I don't know what happened here. Okay, so I'm going to try this next problem, and this one is more analytically. This one's more analytical. So we're gonna have to apply Newton's second law of motion, but in this case I won't draw a free body diagram. Okay, this one says a constant force is exerted for a short time interval on a cart that is initially at rest on an air track. The force gives the cart a certain final velocity v1. The same force is exerted for the same length of time on another cart, also initially at rest, that has twice the mass of the first one. The final velocity of the heavier cart is blank, that of the lighter cart. Okay, and then we have options here. Okay, so let's write what we know. Okay, so we know that a constant force, so we have two different scenarios. So that means the force 1 for scenario 1 is going to be equal to force 2 for the second setup, and that is just F, right? Because it's the same for both. So we have short time interval. The cart is initially at rest. Okay, so then we know that V initial is 0 meters per second, and because there is no indication that for the second setup the cart is already moving, then we'll say for both cars. Or sorry, for both setups. I'm not sure that's spelled correctly, but whatever. And we know that the velocities will be different, right? So we can say V1 is different from V2. And we're also told that the time interval is the same. Same length of time. Okay, so then we'll say time 1 is equal to time 2, which is simply time. And the last thing we were told is that the second setup, for the second setup, the cart has twice the mass. Okay, so we'll say mass 2 is equal to twice mass 1. Okay, that's what it means. Before we solve it, I want you to think of it using common sense. Okay, ignore the fact that it's on an air track. Air track means, think of air hockey. So there's friction is minimized. I want you to think of, what if you were pushing a car with a lot of people in it? No, well, the setup is light of the first time. So you're pushing a cart with no one in it, okay? And then you needed to get to a certain speed, whatever that was. Then you have to do the same thing with people on it, 5, 6 passengers. Would you have to push for a longer period of time? Would you have to push for a shorter period of time? Right? What would that be? Well, if we're going to use this as context, the answer choices, so the first two show less velocity, right? So smaller velocity, meaning that these two pertain to a smaller velocity. Let me move this part. That way I have more space. Okay, let's try that one more time. Okay, so these two, smaller velocity, and these two show greater velocity, and this one's the same. So if you were pushing a cart empty for, let's say, 5 seconds, how fast, what is the speed you could reach? Then try the same thing for the same 5 seconds, but with a lot of people in it. I hope you can see that you would go a lot slower. Okay? So that means we can eliminate C, D, E. Which one is it? Well, I think some of you already know because you have twice the mass, right? So then that would correspond to 1/2. But let me show you how to prove it using equations. Substitution. This is a great skill, especially for those of you taking the AP test. And also for the on-ramps, okay? Because there's questions like this. So what are the equations to know? Well, we have, I'm going to use the easy version of Newton's second law of motion. Force is equal to mass times acceleration, and acceleration is equal to velocity final minus velocity initial divided by time. Okay, why do I want this equation? Because they're giving you information about velocities and time. And we know, let's say for setup number 1. For setup 1, we know that force 1 is going to be equal to mass 1 times acceleration 1. Well, the force is the same, so then we can say force is equal to mass 1 times acceleration 1. Let's define acceleration 1. Acceleration 1 will be the final velocity. In this case, they said it was final velocity v1. So it'll be v1 minus v initial divided by time. Time is the same, so just t. We were also told that the car starts at rest, so then there's no initial velocity, meaning that acceleration 1 is equal to velocity 1 divided by time. Now I'm going to substitute here. I'm going to plug in v1 over t in place of the acceleration number 1. So force is equal to mass 1 times velocity 1 divided by time. And they're asking me information about the velocity, so I should solve for velocity. Multiply times mass 1 both sides. So then I'll have, I use the reflexive property, velocity 1 over time is equal to force 1. Oh wait, I'm not multiplying times the mass. Sorry. Don't freak out. I made mistakes too. So I divide by the mass 1. So then velocity 1 divided by time is equal to force divided by mass 1. Then we multiply. Now we do multiply times t. And velocity 1 is equal to force multiplied by time divided by mass 1. This could be a great segue to describe or to talk about momentum, but I digress. Okay, now let's do the same thing, but with setup 2, okay? So setup 2. So we have the same force, right, because force doesn't change, is equal to mass 2 times acceleration 2. We'll take the same steps, are identical, so I'm going to skip them, but they're the same steps, identical. So I'm going to end up with this equation. Force is equal to mass 2 times velocity 2 divided by time. Took the same steps. Okay? Then if I solve for velocity 2 using the same steps, okay? Same steps. I'll have that velocity 2 is equal to force multiplied by time divided by mass 2. Okay. But we know that mass 2 is equal to twice mass 1. So we have mass 2 is equal to 2m1. What I'll do is I'm going to plug in I'm going to substitute this instead of mass 2. Okay? So then I have velocity 2 is equal to force multiplied by time divided by twice mass 1. Then this force multiplied by time divided by 2 times mass 1, this is, I can factor out a 1/2. Okay? So then I'll have velocity 2 is equal to 1/2 times force multiplied by time divided by mass 1. Now I want you to look at these two. Velocity 1 is equal to this. Notice how they're the same thing, okay? So what I'll do is I'm going to plug in. Okay, I'm going to plug in. Instead of this expression, I'm going to plug in velocity 2. So then we'll have velocity 2 is equal to 1/2 velocity 1. There's my answer, as expected, right? I think this is, you should start with common sense, and then if you need to solve it mathematically, then take this route. So 1/2 times v1 is the same thing as v1 divided by 2. That's it.